It has been hypothesized by Max Planck Institute for Evolutionary Anthropology co-director Michael Tomasello and his co-authors that the sharing of intentions was an important factor in the evolution of humans' unique cognitive abilities. However, how did the ability to share intentions become so widespread in human populations in the first place? This is a question of origins. Using recent advances in game theoretic modelling, we model the evolution of the ability to form shared intentions and show that this ability is likely to have evolved at a time when technological and cultural progress offered particularly high benefits to survival, such as might be the case during a period of significant environmental change. Our model is one of multi-level selection. We consider a metapopulation comprising several demes or bands. Each deme is a small human society. Each individual within a deme has a small number of other individuals with whom he has a high degree of interaction, represented by an interaction network. These other individuals could be relatives, friends, or hunting partners. Each individual is either an SI type, who can share intentions, or an N type, who cannot share intentions. Time is divided into generations. At the start of a generation, any given deme has attained a certain level of technological sophistication. From the status quo technology, we model the adoption of a new technology using the following two-player coordination game. Alpha represents the relative within-deme fitness benefits of the new technology over the old technology. Each generation is divided into 2,000 periods, and every period each individual obtains a payoff equal to his average payoff from playing his technology choice, old or new, against all of his neighbours within the deme, according to the game. Individuals and groups of individuals update their strategies so as to increase their payoffs, but occasionally make mistakes. N-types can only update their strategies as individuals, but SI-types can form shared intentions with SI-type neighbours and adjust their strategies together to their mutual benefit. Thus, the new technology spreads across the deme until it is eventually adopted by everyone in the deme. The new technology then becomes the status quo. Here we see technology 2 replacing technology 1, following which technology 3 replaces technology 2. How does the presence of coalitional behaviour by SI-type individuals affect the speed of technology adoption? There are two possible effects we identify: a conservative effect and a reforming effect. For low values of alpha, there is a conservative effect. By allowing SI-types who are playing new to re-coordinate their strategies with the rest of the population, the spread of the new technology in the deme is slowed down. For high values of alpha, there is a reforming effect. By allowing SI-types who are playing old to coordinate their switches to new, the spread of the new technology in the deme is speeded up. At the end of each generation, each deme has attained some level of technological sophistication. Following this, we enter the deme-deme conflict phase. With some probability, each deme is invaded by another deme, and if the invading deme has a higher level of technology than the invaded deme is destroyed and replaced by a replica of the invader. Here we see Deme B being invaded and defeated by Deme A, following which Deme B is destroyed and replaced by Deme D, a replica of Deme A. The conflict phase can represent warfare, conflict over resources, or simply the fact that demes with better technology have higher growth rates and chances of survival in an uncertain world. Following the conflict phase, the individuals of each deme reproduce according to a finite population replicator dynamic. Thus, both within deme selection and genetic drift determine the population shares of SI and N types in the next generation. When alpha is low, that is to say, when within deme fitness benefits from the new technology are low, then demes with high numbers of SI types will fall behind demes with low numbers of SI types when it comes to technological advancement. When demes with few SI types lead in technology, they will outperform demes with many SI types, and SI will all but disappear in the metapopulation. When alpha is high, that is to say, when within DEEM fitness benefits from the new technology are high, then DEEMs with high numbers of SI types will pull ahead of DEEMs with low numbers of SI types when it comes to technological advancement. When DEEMs with many SI types lead in technology, they will outperform DEEMs with few SI types, and SI will become widespread in the metapopulation, just as we see in the modern human population today. Note that the effect of alpha on the share of SI types is not continuous, but rather involves a phase transition. There exists a threshold below which SI is selected against, and above which SI is selected for. The speed of technology adoption increases in alpha. This would be the case even without the possibility of sharing of intentions. However, the switch from a conservative effect of SI to a reforming effect of SI also causes an upwards jump in the rate of technology adoption. The combination of these two effects implies that the emergence and persistence of SI should be accompanied by higher rates of techno-cultural accumulation. Our results suggest that, under low alpha, interdemic selection does play the key role in the disappearance of SI types. However, when alpha is high, SI becomes widespread in the metapopulation, even without interdemic selection, although such selection does strengthen SI's dominance. The main message of this work is that even for simple coordination games, the evolution of SI is not guaranteed. Moreover, the emergence of SI can be expected to have gone hand in hand with techno-cultural progress. For more analysis in the precise model, please see the published work in Public Library of Science, PLoS Computational Biology, 2015.